Hi, my name is Benjamin Sturman, and these are my teammates, Armando Camacho and Frank Azcuy, and this is our project, the Autonomous Robotic Sprinkler System. Current conventional sprinkler systems are expensive, not only to purchase but to install. And while they're automated and convenient, more often than not, they leave dry areas on your lawn and they're not that efficient. Now, you could solve this yourself by going out and watering these dry areas, but that defeats the whole purpose of having a conventional sprinkler system in the first place. So our motivation was to decrease water waste, as you can see even in the photo, and we've all driven past them before. You see a sprinkler that has broken a head or isn't aligned properly, and it's just spraying water all over the place, not even watering anything, flora or fauna, more often than not your driveway or the street. Our second was to design a reasonable cost system for lawn care, but to utilize the most recent advances in robotics while doing it. Our project objectives was to provide a new, cost-effective, autonomous robotic sprinkler that would be able to protect the overall landscape of your lawn so that it would be able to water efficiently, effectively, without you ever having to touch it. And in order to remain completely autonomous, we wanted it to be self-charging. Just like a conventional sprinkler system, you want to set it and leave it. You don't want to have to go out every day and be messing with it. So what we first decided to do was to look and see, are there any products on the market right now that already do what we're trying to do to make sure that we're just not repeating it. And we were able to find 2 products that were similar to what we wanted to do, but they weren't fully autonomous in and of themselves. The first was the water droplet sprinkler, and it's a great little system. You can set it up and it will water when you want, how you want, where you want, but it can't move itself, so it's not really autonomous. The second was what's called the water walker sprinkler. It's really cool. You can set it out on the lawn and it will follow a specific path that you actually set using your hose, but other than that, it can't really do much, and it goes very slowly and more often than not waters your lawn over, like waters too much of your lawn, and adds so much water that 9 times out of 10 actually starts to kill the lawn due to overwatering. So what this showed us was that we definitely want to make sure that our robot was fully autonomous so as to differentiate ourselves from these specific products. So we decided to utilize similar concepts that you find, such as autonomous robotics vacuum cleaners, such as you find in iRobot and iRoomba, but instead of cleaning a floor, we're going to be watering a lawn. Now, these robots, we use them as kind of our focal point to show that this is definitely a feasible product. This isn't something that we're just dreaming up and we're going to make up completely on our own. So this is a little bit of our first proof of concept. And we also wanted to look at a little bit of the details on what involves with watering your lawn effectively. Deep watering of a lawn requires 1 inch of water per square foot. And then we looked up a little bit of a background for our own personal calculations for flow rate and pressure of the average residential homes, depending on the size of the home, which usually is correlation with the size of the yard. And these are what we use during some of our calculations for pathing and other things. So our constraints and considerations were, it must be lightweight and powerful enough to carry or tow the length of hose. It must be able to keep the hose connection always pointing towards its main source of water. Otherwise, your robot's going to get entangled and you're going to find it in one spot watering the same spot on your lawn every day. And finally, it must be exposure-proof and able to handle all sorts of various terrains and weather. Our proposed design is a circular chassis with a powerful 2-wheel drivetrain, lightweight, easy to transport. In case it does get stuck or it does get, an obstacle causes it to stop and be stuck in the middle of your lawn, you want to be able to move it, put it back where it needs to get started, and not have this, giant robot that you have to lug around. And finally, we want it to be weather and exposure-proof. Our proposed design for the irrigation system is a rotating sprinkler head, a rotating sprinkler base that will be used to prevent the entanglement that I mentioned earlier, a hose retrieval system that will pay out and pull the hose back in so as to relieve tension on the hose and the actual system itself. And finally, a variable water valve so that you can adjust the radius of the sprinkler as it waters your lawn depending on what your specific applications are. This is an example of this is just simulation of the mechanism used to keep the hose from becoming entangled. And finally, the software. Built into the robot that we used is an iRobot chassis, and it has cliff detection, pool detection, as well as collision detection. We added a sonic sensor ourselves in order to help the robot be able to avoid obstacles, as well as humans and dogs and other pets that may come into contact with it under the OSHA standards. It needs to be something that's safe for the consumers to use. Finally, customizable programmable paths and fully autonomy. So if you're not the kind of person who really wants to delve much into it, you can just put the size of your lawn and set it, and it will use its own built-in pathing array.
Okay, so before we even started to build this thing, we wanted to make sure that it could deal with all the forces it's subjected to during operating conditions. So you can see here that most stresses are deflected away from the top base plate to the bottom leg bracket. So then we focused most of our attention to here. And as you can see, what we did was we placed a 20-pound load on top of the base plate around here at the edge in order to induce a small torque, because that's what it will be experiencing as it operates. And they're concentrated near the leg joints. And what we did was we designed the thickness of those joints, and we kept the stresses at 2.8 micropascals, or 406 psi. And we have a safety factor of 21.6, so this will run very reliably. So apart from the stresses, the other thing to keep in mind is the fact that we have a strain. So sure, you'll be at a good point in the stress calculations and such, but we want to prevent excessive deformation, which could prevent the bearing or the assembly from working. And we have a thermal analysis, because not only does the base plate rotate to prevent hose kinking, it also provides shade for the interiors of the chassis to keep the electronic equipment inside from overheating with solar radiation. So what we have here was the chassis interior was 190 degrees Fahrenheit, 43 Celsius, and the exterior was 113 degrees Fahrenheit, or 45 degrees Celsius. Hotter. We'll cover that in a little more detail. So, working with water, we did a flow analysis, and what we did was calculate the Reynolds number. And for our specific situation in testing, we hit 2.71 times 10 to the fourth as the value for the Reynolds number, which means it's turbulent flow for pipe flow. And what we did was I used the Bernoulli equation to derive what would be the exit velocity of the fluid leaving the sprinkler head onto the surrounding. So for a prototype construction, it consists of over 12 parts, but the ones we want to highlight are the Roomba Crate 2 chassis, which was meant to actually be modified. Robot was nice enough to give us a discount as well once we pitched our project to them. We have a Gilmore 8-pattern stationary sprinkler. Originally, you guys saw that we had a rotary sprinkler design, but we switched to one like this one, because it actually gives you control over the shape of the watering area. Do triangles or circles or rectangles, however you want. And the reason a clear flow garden hose, it's very lightweight and actually flattens itself when no water is flowing through it, which is what we want. We want reduced weight, and we don't want heated water either. And then the sprinkler support, which consists of 3D printed ABS plastics. So for sensors, the four we want to talk about is the Arduino kit. It's actually housed inside the robot right now, inside the bin tray. The LCD screen, which allows for user input, diagnostics. You can read what the robot's saying to debug. Digital flow meter, it's a Hall effect sensor that counts pulses, and based on the parameters of the fluid, you can change them in the programming in order to calculate the actual flow rate, and this could be relayed to the LCD so you can see how much water you're using per cycle. And the ultrasonic rangefinder. So normally the chassis could only sense objects when it bumps. There's two front bump sensors, but the ultrasonic sensor can see objects from up to 50 feet away. So now we have an extra dimension of security for object avoidance. And this is a simple circuit diagram. We have the iRobot, which actually powers the Arduino, and the robot operates itself at 18 volts. We have to step it down using a linear regulator so it wouldn't fry the motherboard of the Arduino. And connected to that is a flow meter, the LCD, and the ultrasonic sensor paired with the data cables. So you can see we had a very optimistic project, and what really held us back was cost. So we spent close to $500 on this project, and that's not even counting engineering or their research. So that's just material cost, and that's what really held us back. And then programming and pathfinding was one of the more important topics for this project. And what basically is done is that this is our plant, and we have some of it actually implemented. The user would insert an area to be watered, so the dimensions, length and width. And then based on the watering radius, they'll determine the size of the array to be generated. And then the user will then pick the home array element, and then it will follow a column to row watering configuration. And the average time to water, so for the velocity, it can be determined based on the path that the array generates and the flow rate. And the equation down here can generate how long it takes and effectively how fast it has to go to achieve full water coverage. So then for the ultrasonic sensor, it is found at the front of the chassis. If you're interested, you can come up and see it after the presentation. And what it does is it'll see an object, and it'll go left or right to the previous array or the next array, depending on where the home array is located. So if the array is to the right, it's going to want to go right so the hose doesn't get tangled behind the object. And then if it's on the left, it'll do the opposite, just to keep the hose from entangling with the obstacle on the way. And then once this is finished, it resumes its original array, and then it'll go back up and then head back to the first one. This is a video showing that in action. The ray size is reduced just to show. You can see that the ray space rotates. So it's not the time to be up to itself.
So now I'm going to discuss all the experiments that were conducted for this project to kind of validate all the simulations that Armando was just talking about. First, we found the maximum force that the sprinkler legs and the sprinkler shaft assemblies were exposed to. Next, we conducted a battery life testing. We then conducted effective water radius of the sprinkler head. We also conducted a thermal testing with the robot outdoors. And finally, we conducted an overall assessment of the robot in action. So for the first test, we placed the sprinkler leg in the vise, and we added a weight continually to the other end, increasing the weight. And as you can see, we did 5 different trials, and consistently at 15 pounds, they achieved the violent mechanical failure. A similar test was conducted for the sprinkler shaft assembly, and at 28 pounds, there was no visual deflection shown. So it just validates that what Armando was saying, that if there is going to be a mechanical failure within the sprinkler base, it's going to be with the legs themselves and not anything else. Next, we conducted battery life testing. 3 trials were conducted. We programmed the robot to do a simple back and forth algorithm, and we found that the max or the average battery life was 1 hour and 18 minutes. Next, we found the maximum watering radius of the sprinkler head, and we used a tape measure in order to find the diameter, which was found to be 28 feet. We also conducted thermal testing using a thermal imaging camera. The differences that we wanted to show, as Armando previously mentioned, was we wanted to test the temperature differences with the sprinkler base turntable on and with it off, and see how it helped with the radiation from the sun. So on the first image there on your left is the initial temperature of the robot outdoors. The second one shows the temperature of the robot of the R's after without the base on top, and this last image here on the right shows what the temperature is with the base on top, and this just proves that the cover does prevent that direct solar radiation from overheating the internal electronics of the robot. And then finally, the qualitative assessment was done just to prove that the robot was able to traverse the grass. There you go. So as you can see, it is moving on grass right now, and similar to the array that was previously mentioned, it's doing the array.
Looks like sand to me.
You can see the turnstile on the top. The turnstile is always making sure that the hose is pointing back to the water main. Some of the standards that the RS adheres to is OSHA to ensure the safe operation of the robot and its end users, the Irrigation Association to distribute water safely and efficiently while adhering to local regulations, and IEEE for standards and safety of electronic systems within the robot. Some of the qualities that makes this product a global product is the use of multilingual user manuals, universal units, universal power adapters, and the use of industry standard safety warnings. Some of the lessons that we learned while working on this project was the importance of proper planning. We also the importance of setting realistic goals, as you can see in the proposed design versus the prototype construction. We learned that we need to set realistic goals from the beginning. We also learned about team flexibility and the importance of effective communication within amongst ourselves, as well as learned about new technologies such as programming the Arduino and the various sensors on the robot, as well as how to use a 3D printer. and also, last but not least, a lot of patience. For future work, we want to integrate a solar panel with the robot just to make it more green friendly, as well as save some cost for the end customer, as well as redesign the chassis, the overall chassis, make it a smaller footprint, as well as allow it to give it more capabilities. Also, the turnstile for our prototype was a separate thingy. We want to incorporate that with the main chassis for future work, as well as make the materials that are stronger, lighter materials that could withstand water, as well as the solar radiation. We also want to incorporate the hose reel system. Unfortunately, we did not have, due to funding and time, we weren't able to get to that with this project. We also want to improve on the programming to make it fully autonomous, and with the LCD on the front, make it a little bit more user-friendly. Last but not least, we want to give a final thanks to our mentor, Dr. Tosunoglu, the Megasuki Golf Resort, MME faculty and staff, the Arduino community for programming assistance, the iRobot product support, as Armando previously mentioned. They were able to help us out and give us a discount for the robot, and also all of our friends that helped us with moral support and things like that. Just want to thank you guys for your time, and that concludes the presentation. We'll open the floor for questions.
All right, well, I was concerned about that thing walking on grass, and you showed it that it's walking on dirt. But question is, you said that you wanted to, the future thing was going to be waterproof, so that you can't get that wet, right? Now?
Currently, no. The system itself is not waterproof. You can send it to we do have a company that we were thinking about sending it off to, that you can send any electronics to them and they will waterproof it completely and send it back to you. But when we looked at the cost to do that, they wanted quite a bit.
So you didn't test it with water running?
Yeah, we didn't want to risk it.
We knew that it was a bit of a destructive test, and if we did that,
It would have been a one-time video.
Yeah. Now, you think the water thrust will have any effect on the motion?
Oh, no.
That's very minimal thrust?
While I was testing the hose, getting soaked in the front yard, seeing how well the sprinkler worked, it's very minimal as far as stress.
And one final thing is, you said you got to set realistic goals. If you do, you'll never outdo yourself. I'm done now.
The questions I have to ask is, I love your hose, but to be honest with you, nobody uses that hose. If I put a classical hose on a system like this, would this system perform?
We didn't do testing on a more conventional hose design, so we can't give you an exact answer. But on our future work, what we want to do is actually create our own chassis and better design the wheels so it can move in much thicker grass, as well as handle the extra weight of the conventional hose.
Okay. If this thing runs to full extension on the hose,
Yes.
what does it do?
As far as watering capability or its ability to move?
Its ability to move.
That's why the hose reel system is incorporated. Instead of it trying to force an entire length of hoses we've all done when we're trying to water our cars, trying to get that thing go where you want it to go, it definitely has a lot of weight. And what the hose reel system will have inside of it is a small motor that actually retracts and pays out and retracts the hose. So they will be communicating through whether it be wireless or RF. And as the robot says, all right, I'm returning towards home base, it will continue to reel.
It'll pull it
will
in.
be, yes, it will not necessarily pulling the robot, but it will be pulling all of the weight of the hose for it. We thought of that initially. We were like, well, how's this thing ever going to be able to pull a hose around the yard? And I was like, well, we got to have some.
So that unit is going to move from position to position? All the way down your
the hose
yard?
reel?
Yeah.
The hose reel is mounted on, like, the ideal situation would be to mount it on the side of your house, just like where you have a normal hose reel. And typically you want a hose of this.
But I saw your pattern. Your pattern was basically down, up, down, path, down,
Yes.
up.
Yeah.
How are you
Well,
going to do
as
that
it's
with a hose
mounted on the
reel?
house, it will be a hose reel like this, and it will swivel. So as the robot heads to this portion, it will always be pointing directly at it. So even if it's going up and down, it still has a maybe diagonal, not necessarily perfectly linear path between it, but it will be always heading, as, again, the up and down motion, it will always be able to reel in and reel out. It won't have to be trying to reel something that is all the way over here, and the system will down. That's what the swivel portion is for.
And my last question is, how programming friendly is this with the assumption that everybody's got geometrically different yards?
So with that question, what we wanted to do was use Google Maps implementation to find the shape of your yard, and then from there it would be able to map something custom to your yard. So that's actually a really big goal. Take a team of programmers maybe wants to come up with some sort of solution. It's just us giving them other obligations to commit to. But for now, we do have a custom program with that.
And how easy is that to program?
It's very simple to program.
Can my wife program it?
Well, with the way
Computer
we
illiterate.
like the standard experience.
You're walking down a
Well,
dangerous slope.
It's funny because this came up during our first presentation. What we said is, as of right now, it is, obviously we want it to be fully autonomous and for people to be able to play with it and delve into it, but as of right now, it's marketed towards the conventional lawn, which is your, front yard, which is generally a square or rectangle.
Not mine.
Obvious. I do realize that not all are, but in general, we are gearing more towards just the general residential home. It's obviously not meant for large yards. It's not meant for, people who, I know a lot of people have a lot of bushes and grass and things, and I'm like, well, that.
Yeah, there are limitations, just like, those very expensive 980 Roomba vacuums that you shouldn't really leave a lot of obstacles in the way because it will affect this.
Yeah, how tall a grass can it run on?
So when we did
Yeah,
testing
yeah.
about like half an inch, and we blame mostly.
Half an inch?
Yeah, the wheels were the biggest factor. So this thing actually has a lot of power. The stool that you saw in the video, it was able to drag that thing, but it just couldn't find the traction because of the way the wheels are set. And we tried doing modifications, but the chassis is so modular and the tolerances are tight. So adding any more modifications to the wheels would be a lot of trouble, which is in the future we're going to design a whole new chassis from the ground up.
Definitely, you have to adjust the wheels. Obviously, the ones that are on there are designed for carpet inside. And when we initially tested it, we obviously took it, we put it on the grass, and it was running around fine in typical Florida grass. Then after we had added a few more components, a hose, a few other things, it actually, like you said, there was a lot of torque. It would actually rip up portions of the grass while it was trying to get the traction. But the wheels themselves, if there had been a way, like you said, to modify them to have maybe some spikes or something else, it easily would have gone through the grass. Just as of right now, the depth isn't there.
Okay, thank you.
Talking about wives, my wife bought me a couple of hoses that they're cloth and they fold up